Good morning, everyone. Welcome to today's webinar, Digital Twins of Society, HPC-Powered Simulations. My name is Božidara Pellegrini. I'm here on behalf of NCC Slovakia, co-organizing this event together with NCC Portugal and NCC Norway. Before we begin, I would like to inform you that this webinar is being recorded. The recording will be published afterwards on our YouTube channel and the NCC Slovakia website, so you can revisit it or share it with your colleagues. Today, we'll explore how artificial intelligence, multi-agent simulations, and cultural cybernetics are used to model the emergence of belief systems, social movements, and societal resilience. We are proud to host this webinar on such a relevant topic, especially considering that our Slovak supercomputer Devana is being used to power the HPC calculations behind these advanced simulations. I would also like to encourage all of you to post your questions in the chat at any point during the presentations. We will address them all in the Q&A session at the end. So without further delay, let's begin. Before I hand over the floor, let me briefly introduce our first speaker. Professor Dr. LeRon Shults is professor at the University of Agder in Norway and scientific director at NORS Center for Modeling Social Systems. He holds doctorates in educational psychology and philosophy of religion, and his research focuses on cultural cybernetics, modeling group identity, religiosity, and extremism. He has published extensively and led projects applying simulations to understand societal change. So, LeRon, please, stage is yours.
Thank you very much, Božidar. Thanks for the invitation and for the collaboration. Let me see if I can share my window. Go. Let me know if you can't see that. Looks good?
Yes, perfect.
Okay. Yes. Thank you again for inviting Justin and I for this presentation. We've been looking forward to it very much. This particular model we're very excited about. It's an advance on the other work that we've done. You have, let's see, you've already introduced us, so I'll skip this slide. Some of you may recognize a couple of the characters on the bottom there who've been in Bratislava for quite some time. The overview, I'm going to try to go for about 15 minutes or so describing social simulation in general and what it means, how our approach to modeling belief systems and social movements. And then Justin's going to dive into more of the technical details, and we hope to leave plenty of time for Q&A. So here at Culture Pulse, our passion is utilizing AI technology to address societal challenges. And we've really been lucky to have a lot of exciting opportunities to do so. And I had a lot of great funding, great press, great interaction with important actors throughout the world. Most recently, UNDP in Palestine, as you can see there. We've also done modeling on a wide array of other topics. You can see some of them listed there, some of our early ones on various social psychology theories, which have been then fed into the more advanced models you'll hear about today. We've also addressed issues of interest to us personally based on our educational and professional background, issues related to secularization, the Syrian refugee crisis. Here in Norway, we've had several groups heavily involved in that. COVID-19, sustainability. As Božidar mentioned, I'm a professor of global development, so these are issues that we try to address using these tools as much as we possibly can. The UNDP collaborations, which I already mentioned briefly, most recently with in the Balkans, we did a model of that region in which we studied outcomes related to vertical trust, the population to institutions, and horizontal trust between different ethnic religious groups there. In Palestine, we developed a model that tried to measure the resilience of the Palestinian people. In both cases, working with stakeholders in those regions in order to develop the models so they would be as realistic and policy relevant as possible. The model you hear, as I've already hinted, the model you hear about today is even more advanced than any of those models. We'll be excited to test out the simulation runs on the high performance computing cluster there in Slovakia. Justin's going to say a lot more about this particular model, so I'll just keep making hinting allusions to how excellent it is, and focus more broadly in the next few minutes on what social simulation is in general. Yes. The first thing to say is it does use AI, but not in the traditional sense of machine learning, where in machine learning you can think of it as a single agent that's really good at doing one thing, like reading or playing chess. Our approach is multi-agent AI, so you can imagine populations of thousands, or in the case of Slovakia, millions of agents simulated in a virtual society, or a kind of artificial laboratory where you can test and explore the different mechanisms that are driving outputs you're concerned about, such as education level, economic stability, social cohesion, and so forth. So what we do with those agents is put them in artificial societies. They're more psychologically realistic than typical machine learning and game theory approaches, because built into the cognitive architectures of our models are dimensions such as motivation, anxiety, in-group attitudes, concerns about economic security, whatever variables we need in order to be able to test the particular policies of interest to the stakeholders. Then they're placed into realistic networks, so they're not these agents don't just randomly interact as in game theory. They're going to interact differently depending on whether they meet someone who is ideologically similar to them, or somebody in their region, or someone of the similar age or gender even. So far more realistic interactions within these artificial societies. And then of course, they also interact with their environment. That means you can turn up for example, in the environment, the economic pressure, or you can add the number of immigrants flowing into the region. All sorts of parameters can be adjusted in the environment, which then the agents interact with as well as they move through the different runs over days or weeks or months or even years. So what makes social simulation so exciting from a scientific point of view is that you're moving beyond simple statistics into simulation. So it might be interesting and important to know that in Slovakia, I'm making up the following statistic, that women between ages of 20 and 25 are employed in data science at 13% in 2025 July, right? So that's a snapshot of a particular set of variables. What a simulation lets you do is turn it into a movie, so you can discover how you got there, what the complex factors and mechanisms are that drove to that particular picture, and then run out simulations in the future following different plots if you wanted to, for example, to increase the number of women in such employed positions, or to decrease it. So this is often referred to as generative social science, because it's not just analyzing, it's actually generating. You're getting toward causality. How is that possible? I mean, this is the holy grail of social science, to get to causality. It's possible in social simulation because you don't program into the model the output at the macro level, the population level shift in, for example, feeling of economic security, or trust of the government, or willingness to cooperate with culturally different others within Slovakia. You don't program that in. All you program in are the agents at the micro level and their interactions. So if you can grow the macro phenomena in your virtual laboratory, you have a plausibility argument that you've got at some of the main drivers or mechanisms that lead to that phenomena you're interested in. Here's a way of visualizing it. In the first box there, you can imagine the simulated agents. So in this case, it would be 5 million agents. They'll have variables such as gender and age, ideological background, economic status, employment status, and so forth, set into a virtual laboratory or an artificial society. Then there'll be a whole set of intervening variables. The conditions or parameters can be altered, where, to use the example I used above, there might be economic stress, in the environment, or immigration, new immigrants coming into the region, or there could be new policies that make it easier for certain people to start companies of a certain kind, for example. So at the sort of structural level, those variables or those parameters are changed, and then the agents interact, and you run hundreds of thousands of simulations to see, under those conditions, how do you end up with the different kinds of outputs. Then the last box is the increase or the decrease in the macro level of variable or pattern of interest that you have. So if you want to know, for example, how to improve a sense of economic security, then that would be your output. You would run simulations to try to identify the pathways to achieve that particular outcome. So fine, this is my last slide before I turn it over to Justin. All of that means that these simulation experiments, which again on super high computing clusters, we can run hundreds of thousands, even more, to explore the possibility space of the Slovakian population, the possibility space into the future. So we want to know the conditions under which and the mechanisms or the levers that are driving individual or social variables. So in much of our work, that variable is conflict or cooperation. But in the case of the model we're developing in Slovakia, it could be a whole host of things related to educational outcomes or economic flourishing and so forth. This then enables scenario forecasting, prediction, and optimization experiments. So optimization experiment means once you've validated the model and you know where you are right now in July 2025, and you have an idea where you want to be in 2026 or 2027. The computational model, then the algorithms can search the possibility space for finding the most effective way to get to your outcome. But it also shows you that if you get that outcome, you're likely to have other outcomes that are impacted by the complex nonlinear processes of the whole system that maybe you hadn't thought of. So it provides a really powerful tool for policy stakeholders, not just to predict, but also to analyze what's going on in the system they're concerned about. This is important for obviously because it's far less expensive to test in an artificial society than in the real world, but it's also ethically more appropriate because you can't just spend millions of dollars and put students through different types of programs or bring immigrants into the country to see how it affects people. There are ethical limits and to what can be done in the real world, and testing some things just is not appropriate. What this model will provide is a digital twin in which all kinds of explorations and simulations and experiments can be run to explore that possibility space and hopefully open up new dialogue for policymakers. So with that, I'll turn it over to Justin. And Justin, it's probably easiest if you just let me know when you want me to click to the next slide.
So thank you very much, LeRon, for this fascinating presentation. Just a quick reminder to everyone, if you have any question, please write them in the chat and we'll come back to them in the Q&A session at the end. And then now I'm happy to introduce our second speaker. Dr. Justin Lane is a co-founder and CEO of Culture Pulse AI, scientific director at the DEC Institute in Bratislava, and affiliated researcher with the Slovak Academy of Sciences. He completed his doctorate in cognitive anthropology at Oxford and is a pioneer in multi-agent AI, digital twins, and modeling the spread of beliefs and misinformation. His work has appeared in Wired, BBC, and the New York Times. So Justin, please, you can go ahead. We can see the screen. We cannot hear you yet.
Oh,
Over here,
Yes, now we can hear you.
but can't see the share screen, even though it seems to be sharing.
We can see it, Justin. We can see the screen.
Oh, could you? Oh, okay. I
Yeah.
thought you couldn't see the screen. Sorry, let me reshare. You can see it now, yeah?
Yep.
Yes.
Okay.
Perfect.
So back to where I was. Thank you very much for the kind introduction. I'm going to kind of build off of LeRon's earlier presentation almost as a sequel, and try and build into this and get into some of the more technical details, because LeRon and I have been collaborating now for over 10 years, and working in these areas. And generally our collaboration has worked so that LeRon is working more on the policy aspect and some of those more social, scientific, humanitarian nature of what we do, while I've focused more on those more technical aspects and the implementation and actual sort of building and execution of these large models, on different systems. And LeRon gave a great overview of the use cases where this is very useful, and where he and I have worked over many years together. What I'll focus on is the one that he kind of hinted at earlier on, which is the Slovak digital twin that we're working on, and you'll see a lot of the of our discussion around how this relates to conflict and policy, because the reason why we wanted to build this digital twin was really to investigate issues of social cohesion in Slovakia. Kind of scrolling through the list of people in the group, it does look like a lot of people are probably local here in Slovakia. I'm also now based in Bratislava and have been for the past 8 years. Um, and so most of the people that are in attendance from either Slovakia or the region know that polarization has been increasing, in the political sphere here for quite some time. And the work that LeRon and I have done in places like Lesbos during the Syrian refugee crisis, Northern Ireland around the paramilitary activities in Northern Ireland and the conflict there between the Protestants and Catholics, the work we've done in the Balkans and Bosnia and Herzegovina, the work we've done in Palestine, and in the West Bank, those are examples of what happens when social cohesion breaks down and polarization is no longer an issue of the media, but it becomes an issue of conflict. Currently, Slovakia has an issue in terms of polarization and how people feel about aligning themselves with a sort of European identity that's 4 times greater than any other country in the region. And this presents a problem that I think this simulation approach is uniquely capable of offering some sort of actionable insights on, particularly around the issue of what are those wedge issues, those issues that are going to really polarize and separate aspects of society that could result, for example, in physical violence between groups and things that are riots. And I know that for a lot of people, um this kind of discussion is, on the one hand, many people find it uncomfortable. On the other hand, many people find it implausible. But the work that we've done, for example, with terrorist organizations, in Northern Ireland, they will all tell you that a month before the war started, none of them would have thought they would have been in war. And then a month later, they were in a war that lasted for 40 years. And so it's much more important to be prepared and to address these sorts of social issues before they become a problem, particularly when you have, other countries that are working in the area of what they call foreign malign influence, or inserting information into Slovak society that's designed to polarize society. That's what they're looking for, really, is to break down the social cohesion here. And the security risks of that, the economic risks of that, the political risks of that are so insurmountable that we really wanted to try and address that more directly in Slovakia. And naturally, with 5.5 million people, more or less, um, this becomes a really interesting technical challenge as well that you need to leverage HPC systems in order to solve. And so I'm going to talk a little bit more about what that actually looks like. LeRon mentioned that in these multi-agent AI systems, we're not using the traditional machine learning. That is to say, we're not really focused on back propagation style machine learning systems. There's 2 reasons for that. One is that the data that you need to ingest in order to get a good model fit of a human belief system typically is so large that you cannot actually scale it to a population level. Right, so you can create one chat GPT, right? You can create one Llama, one DeepSeek, one Gemini style large language model that can really seem very human. But when you do that, you have too much information in that system, right? You don't need to have every agent in your simulation have a deep understanding of, physics in order to run a simulation on social cohesion, right? There's too much information in the large language models. And I know that a lot of people have been saying, oh, the agentic nature agentic AI is the future of AI. And I kind of jokingly say, I'm glad I made those mistakes, 10, 15 years ago, when I first started and was first proposing multi-agent artificial intelligence frameworks. I wasted a lot of Oxford's money when I was there as a doctoral student trying to do that approach. It does not scale and it doesn't work. And I'm going to give some data about this and how we've seen this. And one of the reasons why we're really excited to be partnering with the National Supercompute Center and utilizing the Divana system in particular. And kind of get into that discussion at the very end of the CPU versus GPU and why they're even why so many supercompute systems are over allocating, in my opinion, GPU architectures. And this gets down to the art of the science, as we say, right? When LeRon was discussing those psychological mechanisms that we're using, choosing which ones are important to build into our cognitive architectures, that's where it's a bit more of an art than a science sometimes, right? We're trying to really bring in the studies that have been done in the lab in psychology or in the field in the field of psychology and create modular functions or functions in the computational sense that mimic psychological modules in the cognitive sense. So the information processing module of a psychological study that's being more exposed, some sort of heuristic or some sort of bias in the way that the calculation is done, we're trying to instantiate those models as micro models within a larger cognitive architecture where it's very functionally programmed in. All right. This also allows us to pull in psychological properties like personality variables, where we can then use that as an input in the function that can weight, the output in some way. Similarly to how in system dynamics models, which can be really reduced down to differential or difference equations, that you will add different additional variables that could increase or decrease flow rates within that model. Our system is doing the same, but it's doing it at a more computational level that also is including the if-then logic that's much more well handled by an agent-based approach or an agent-based simulation that operates on a CPU, as opposed to the more time-based differential equation styles that are more common in system dynamics models and very well formulated for GPU architecture. So this is starting to already get into that, and hopefully you can kind of see where we're going with the CPU versus GPU. The systems that we're using as well to understand what that psychological environment looks like includes a massive amount of data sources from the internet. We in this project are really just focused on social media and Slovak media and surveys of the Slovak population. And the surveys are really where the meat of this project is going to lie. That's really where we wanted to focus our scope for a number of reasons. One of them being, we know that we can get a statistically representative sample of the country at the level of the kraj, or I guess you would say the state. The analogy would be like a state in the United States, being the kraj in Slovakia. So we'll have a representative sample of each one of the states within Slovakia, and then can build out our understanding statistically at that level. So we don't just have to assume the country is one country. In fact, the political, social, cultural differences of Slovakia are some of the most diverse in all of Europe. And so understanding that the northern mountain regions are very different from Bratislava in a lot of these areas is really critical and important. And it's something that also really backs up why we're utilizing distributed systems of agents in order to simulate this approach on an HPC system, is because you need to have variation within your agents. You can't just assume any one agent is equal to another agent in their attributes or their actions, their concerns, and their biases. You need to have those biases mapped out and those differences mapped out because they are very important, actually, to the reality of what we're looking at when we're trying to simulate issues of social cohesion and in the effect of disinformation. So the system that we're bringing to bear on this really deconstructs text patterns that come out of social media and the media. We can pull this into 93 different dimensions. So while we're taking texts in, we're then decomposing these into different psychological dimensions, where we've utilized a proprietary algorithm actually that can convert those in, and we've validated this over and over and over again. It's been utilized in peer-reviewed research as well. The validations have gone through peer review and been published in different journals over the years that allow us to give every agent or our understanding of every agent the psychological dimensions that are necessary to understanding aspects of polarization. And one of the key things that we're going to be building into this model that are going to be useful for this exercise actually are morality. And different dimensions of morality are extremely important for polarization. And we see them here that moral issues around authority, for example, are very polarizing to society. And so we can get that data from social media and from taking a large, NLP, big data approach, and then also supplementing that with survey data so that we can get a ground truth using psychometrically validated surveys. So we're bringing that sort of psychological accuracy from the lab out into the field, and then at the same time bringing the data down out of the cloud to touch the ground, right? And by doing this, it really gives us an understanding of what the reality is in these simulations, so that, as LeRon says, when we're moving from picture to video, we need to make sure that we've taken the right picture first, and then we can try and fast forward into the potential realities that may happen and look at what's going to end up going on in the future. And this basically allows us to go from social networks, also in incorporating news feeds. So in the past, we've done this. In the past, the largest project that we had done in this was going back over 50 years. We were using 85 of our 93 categories, and we had about 50 million articles that we had analyzed. In this one, we're still gathering the data, and we do the data gathering now in real time. So we've already started gathering the data. We have data from Slovak media going back to the 1990s, and it's updating basically every hour. And it's been updating every hour for over a year and a half before we even started the project. So we're sitting on effectively the most real-time data set of Slovak news media that you can find. And this is going to be what allows us to understand the initial conditions of the simulations that we want to put forward and that we really want to investigate, because we can make that connection from the reality to the simulated world, and that really is the foundation of the digital twins that we have, right? And the core use case here, as we mentioned, as LeRon mentioned, is the low risk testing in an AI environment for things that would otherwise be problematic from an ethical standpoint to do in the real world. The way I would put that is we have an experimental and safe policy sandbox. But we also have a social sandbox. We don't just need to test policies for different governments or different ministries. That would very much be possible, so that we could try and help them understand what the repercussions of their actions would be. Many government organizations really are just trying to use best practices. And this is true not just from a policy standpoint and from a government standpoint. It's also true in regards to, once a policy is in place, how do you actually action on that policy? So throughout Europe, there are already policies on misinformation and disinformation. But how do you action on that is a day-to-day decision that needs to be made by decision makers in as intelligent a way as possible. And there are different, in the case of misinformation, which is one of the potential use cases that we're utilizing with the funding on this project, is if, let's say, 5 different narratives, 5 different types of disinformation are going to be spread in Slovakia tomorrow. Most of them are going to be useless. Nobody's going to care about them. They'll get almost zero interaction in the media, and it's going to have absolutely no effect in the real world. One of them, though, may just hit at the right place at the right time, those psychological factors that trigger conflict and polarization here. And something needs to be done about it, because it could, become a larger social issue or threat from a security standpoint. And this, understanding what those could be before they happen, can be something that's very useful to front run this from a security perspective in the European Union. And this is one of the things that we're just looking at is kind of just saying, what's the what if in terms of social cohesion here? What are the worst case scenarios, and how can we try and address them sooner rather than later? And to do this, we really need to pull out what those important psychological factors are, not just during the simulation, but before the simulation, right? As we're analyzing this data, as we're going through and pulling out all of these different dimensions that we have and that we'll have on this one, this allows us to basically look at a correlation matrix of over 8,000 different insights that we can bring to bear in this simulated environment, and really understand what are the statistically significant correlations that we need to potentially focus on, and what are the ones that we can largely just wash out and are not particularly interesting for us. These are the different aspects of the profile that we go through, right? So everything from demographics, psychology, personality, financial issues, linguistic threat issues, etc. But the big ones that keep coming up for us are these moral issues. And in the data that we've gotten in the past version of doing the World Values Survey with the DEC Institute, we found that those were actually some of the most critical issues in Slovakia when it comes to how it's affecting social cohesion. And this is one of the core focus things that we want to focus on in the simulation itself. So there's a general understanding of how we're pulling the data in, doing the language decomposition, and then some of the use cases we've done in the past. Now, to get into to some of the technical details on this, really there's a big question of how do you initialize a nation? And I think there's even a question of should you initialize a nation? Both from the computational or let's say epistemological standpoint, and of course there's also the one from the ethical standpoint. And I think that happy to address some of the ethical ones in the Q&A. I think because there's so many different things that could be raised on the ethical side that I usually kind of let the audience push back on that and go take that where they want to go. But it's something we've given a lot of consideration to. But in terms of how do you initialize a nation, and do you need to epistemologically, I argue that the answer to that is yes. A lot of policy models are very toy models, right? They run on small scale, laptop style computers, and they're not particularly large in terms of their size or complex in terms of their interactions or the mechanisms that are driving the model. And that's often done because of computational resources, right? They don't have access to an HPC cluster, or their methods do not allow them to scale. And that's extremely common for a number of reasons that I'm going to get into in just a second here. One of the things, though, that is always in question is whether or not the behavior of your model is still the same when you add agents into your model. So if you're doing a large-scale simulation on an HPC cluster, your memory thresholds allow you to grow your population size to the real-world population size. And there are some cases where even within a social network system, if you're looking at a scale-free, like a small world scale-free social network, you're going to naturally have clusters inside of that network, and that's going to be what defines that network. Now, if you're working within a network construction that is a more randomized, like Erdos-Rangi arrangement of the graph network, when you're dealing with that, you're going to have certain information patterns that are not as, built into the cliques and the modules of the social network itself. So information spread is not as insular, and you get more information passing between clusters than you do within clusters. Right now, if your simulation is only large enough to handle, let's say, 30 agents, and you are effectively creating what is a random network, an approximation of a random network that should be scale free by all of its mathematical properties, but is ineffective in its information dynamics because of its size, you need to utilize an HPC system that has a memory threshold and the ability to go across different nodes so that you can simulate several million agents where you do get the flavors that pop out naturally from social networks and information passing within a social network. So in the systems that we have, we're really focused on those dynamics in particular, because this is how we're learning, right? This is how culture is built. This is how information spreads, is by information going across social networks. And that's not just to say online social networks. In our system, we're very much trying to simulate offline social networks and approximate those. And that becomes particularly important for us. So what we end up doing is creating and initializing a social network. And there's a role and a place for social media here that you can utilize. But more importantly, we can approximate these social networks based on a mixture of geospatial data, geospatial information, psychological information such as extroversion and personality traits of how many people you're most likely to speak to, and then cognitive constraints of the human mind. Everyone here, for example, is likely to have about 150 people that they talk to every year, that they're close to, right? That they would actually, have a conversation with. Not that they know, but that their social network size is effectively about 150 a year. The number of people that you're close with or would talk about finances with is on average about 4 or 5 people. The number of people you speak to on a weekly basis, going out to dinners or coffees or something like that, is usually about 15 outside of, the forced interactions that you may have at work. And then the number of people you're speaking to once a month is about 45. And we know why this is it's because of the cognitive constraints in human memory. We can only remember about 7 things at any one time. This is why phone numbers are clustered into clusters of 2, 3, or 4 digits, is because we can't remember the entirety of the number, but we can remember kind of the song as to how you would say what your number is. And there's a number of different ways that you can do this. For example, my wife is bilingual effectively at this point and speaks both English and Slovak, but she cannot tell me her number in English without it just completely hurting her brain, because she always says it in Slovak. And so she says her numbers in Slovak, and she doesn't really know the numbers. She just remembers how to say them in a certain order. And when she has to do them in English, it hurts her brain. So at this point, I know enough Slovak that she just tells me the numbers and I can do those numbers now. But initially she couldn't even type. She just get out of the way. I have to type it into the computer or whatever needs to be done. I'll put it in the phone, because that's just the way our memory works, right? It's rote memorization, and we can do that, and the working memory can only hold so much at one time. And so our ability to transfer that information, effectively our brain's random access memory, is extremely limited. And when that ends up happening, that also happens in conversations. So I can have a conversation with one person, which has 1 link. I can have a conversation with 2 people, right? And that has 3 links, right? If we have a conversation with 4 people, you end up having 1, 2, 3, 4, 5, 6 links. So once you get to 5 people in a conversation, our computational ability to store all of those links in our memory break down. And this is why conversations that hit 5 people will split to 3 and 2. So the next time you're at a pub and you're sitting around the table and there are 5 people there, you just watch how long they can go in an active conversation with all 5 of them participating. Usually within about 2 to 3 minutes, our brains are going to be so overloaded that we're going to have to split the conversation into 2 and 3. And this is an example of the kind of mechanism, the kind of functions that we're building into these simulations that allow us to simulate stable social network structures over time without predefining the network. So we do not need to predefine the network. We can grow the network, and then the network can be stable and still have human realistic functions as it's simulated in future time, and can still be dynamic. You can still simulate divorces, the addition of new people, the dropout of older people. You can still have those dynamics and still keep it psychologically realistic, and therefore sociologically realistic, because what determines our social network structure is, more than anything else, our brains. And it's these aspects of AI that where our definition of artificial intelligence really comes up to the level of artificial intelligence, is because we are achieving psychological realism in key functions, and utilizing those systems to actually be distributed and do that. Now, within each agent, of course, we also have the belief networks, and these are doing a lot of work inside of this. So, here we have a visualization of it, but list-based approaches to social to information is not great. Embedding spaces are great at defining the semantic space, but not always the conceptual relationships. And psychologically speaking, there is a significant difference between a semantic space and a conceptual relationship. Right, the semantic space of 2 terms could be almost exactly the same, or it could be the same within 2 people, but 2 people may not have the same understanding of the meaning of that term at that individual level. right? So when you're creating those embedding spaces in AI or in natural language processing, what you're effectively doing is creating an average of the system that you have, right? You've created a single model of all of the data, and which is, so to speak, I would argue, a akin to a measure of central tendency, like a mean or a median of the population. In the systems that we want to look at, though, we need to get those individual differences. And so we have to decompose that down to a more individualized level. And this allows us to have millions of agents, within each agent having, N beliefs. This allows us to really scale into that national level simulation. For all of the data that we're looking at, for all of the locations that we're having, we're also looking at the news that's there, and this can allow us to create systems where we are going to use traditional machine learning algorithms to figure out what the important psychological factors are of those belief systems that are really predictive of different breakdowns in social cohesion or increases in polarization. So as an example, right, these are some of the kinds of data that we're looking at, some of the psychological factors that we're looking at. And looking at, do certain kinds of events correlate with different aspects of psychological emotion, and finding out that, at least in one of the preliminary data sets we've analyzed on a similar model here going into this project, that yes, there's a correlation, for example, between the number of events and sadness, but that other aspects, including other aspects of negative emotion, do not actually have correlation. So here what we've done is taken the correlations, and if there is if it achieves statistical significance, there's a link there, and then the link weight is the correlation coefficient of the actual relationship, and just using this really as a way of visualizing this and figuring out what are the most key aspects of psychology, and are they related to our core aspect, which are events related to polarization. And what we find is that, there are certain here, but like some of the most important psychological factors are not necessarily there. We can also do the same thing with morality, right? And finding out that our core metric does not have a lot of different things, but the way that, for example, the highest correlation that we're seeing is that the number of polarization events are related to issues of fairness. But the way that fairness is defined is unique to every culture, and that these issues of fairness are related to in-group, right? They are related to harm, and they're related to aspects of revenge, but they're not necessarily related to issues of authority. Right, and so this helps us from a more qualitative standpoint to understand, as we initialize the simulation and as we move forward, what we can do there. So there are a lot of frameworks from a computational perspective that you could use to implement these kinds of models, right? From a in terms of what's happening, I mean, people are utilizing, some of the raw coding, and they're just creating their own simulation engines. But most people are utilizing simulation engines that are more out of the box, right? They're looking at AnyLogic, they're looking at NetLogo, they may be looking at Simudyne. There's Repast. There's, Python has the Mesa format framework as well, with the increasing use of LLMs. There are now LLM agentic frameworks, almost all of them based in Python at this point, just because of the popularity of Python amongst the data science community more than anything else. But there are a couple of reasons why most of these frameworks, for those of us who are old enough, I'll also put MATLAB on the list, even though a lot of them may be very useful, and a lot of them are going to be well known to the university researchers who are using HPC systems, those generally do have a lot of setbacks. And the core factors there do end up being memory, message passing, and distribution. And if you're really going to utilize the most out of an HPC system, you need to know that you have optimized memory, message passing, and distribution. Otherwise, just do it on a really large single box. If you can't, address those three issues, you're really not getting what you need out of an HPC system. And when you're simulating an entire nation, you do have a system where you need to have high levels of memory, not just at the individual agent level, but because you have 5 million agents with their own memories, you need to have a very high, RAM access in the area of terabytes, just in order to initialize and run that model. From a message passing perspective, in order to, again, access all of that memory and have the computational power where the CPU can run those architectures at the agent-based level, you do need to have it distributed across nodes more often than not. When you're looking at 5 million agents with this level of complexity, you surely are looking at something that needs to be across multiple nodes. And this means that you need to use message passing for distribution. And in some cases, I would separate distribution out because you're going to be running some of those models in parallel, and your data sets need to come in to a single point as well. But I'll set that aside for now for the sake of time. Utilizing Java is typically the framework there, right? Because the agent becomes the object. And so object-oriented programming languages do become your go-to there. And one of the other reasons for that is that the hardware to software relationship becomes very problematic in some of them, and the reason really becomes you become thread locked, right? So you can, in Python and Mesa, create simulations and utilize multi-threading libraries in order to artificially parallelize them across an HPC system. But if you have a memory issue where your memory threshold needs to be so large, you actually need to go across multiple cores, that becomes more and more problematic. And there are some areas where you can utilize in Java, for example, AnyLogic is raw Java with a simulation engine. NetLogo is technically Java on the back end. But a scripting language that an interpretation language on the throughput, where what you're doing is effectively opening a JVM. And if you're opening a Java virtual machine across multiple cores, you can try and utilize those cores effectively, but you cannot distribute across nodes in those systems, right? Which limit that our ability for us to scale to 5 million agents, particularly when they're cognitively informed. So what we're looking at is using a system called DMason. The Mason framework and the third release of the Mason framework a few years ago, I believe it was the third release, I could be wrong there, has a distributed functionality.
I'm sorry, Justin, just a second.
Yeah.
I believe we don't see your screen anymore. Can you check that, please?
Oh, okay. It decided to turn me off there. Is it better now?
Great, it's back on.
Okay, that's very weird. Teams is fussy with Linux, so that's yeah. So there we go. So maybe it was around when I changed here. So this is one of the reasons as well. These memory threshold issues are one of the reasons why you cannot use LLMs and GPU architectures. You can create great agent-based models with large language models as the underside part of it. But what you end up getting, though, is that as you scale your agents, you cannot effectively simulate a large society. So for us to run 5 million agents, and this data comes from our partners actually at AWS, where we've done a lot of the work on the corporate side and for different government consultancies and our partnerships as well with Slovak Academy of Science. We're looking at how we can try and basically move to the local Slovak supercompute system there as we move forward, because the hyperscalers are really focused on the GPUs, and GPUs are great if you need large language models, but to run large language models, the inference time to actually look at those interactions as you scale, even if you have access to, if you're looking at let's say 100 GPUs, you're still looking at interaction times of 10 seconds per interaction, which means that we would have to be running this model for a year or more to even get close to any sort of interesting interactions in the simulated time space. Those agent-based models are not fast enough to do that. That assumes you could even store all of the agent memory inside of the HPC system that would run on GPUs. So there's a time and a place for the GPU for sure, but there's also a time and a place for the CPU. And GPUs, in my opinion, have been overinvested, because when you're utilizing psychologically realistic agents that are more constrained and interpretable, that cybernetic agent as opposed to a backpropagation agent, you do get better interpretability because we have predefined architectures. You get speed, scalability, cost effectiveness, you get accuracy. You also get the ability to build in during your simulation runtime at the agent-based level Boolean logic that can run extremely fast. You don't have to wait for an additional iteration or interaction between time steps of your model, because you can build complex decision trees that can interact with different aspects of variables at the agent level in Boolean logic, so that you get a lot of really flavorful but highly accurate behavioral repertoire inside of that. So this is a bit of an understanding just in terms of like where we're going with this. These are the kinds of models that we're looking at, right? These are models that come from psychology. They've been investigated psychologically. We know what the weights, we know the significance values of all of the different variables here. There are psychologically validated measures for all of this that allow us to get to the within group consensus that really models personal beliefs at an individual level that build up that within group consensus and what looks like when it breaks down polarization and conflict in society at the high level. And this is what allows us to really understand at the agent level how interactions at a social level, even though let's say everyone here, this purple group is the boundary of Slovakia, and these are agents that are representing these groups. And let's say you have in the red here, you have different agents that are a subgroup of a different set of beliefs that are interacting more often with each other than they are between the two different groups. And this red group could be, let's say, people in Bratislava, and the blue group could be, people outside of Bratislava in more rural areas, more rural neighborhoods, that you can get these sub pockets of information where the information doesn't spread. And what you end up having is a single sort of line, a schism point in society, where if you're going to push certain information into that, the system can simulate that it's going to spread more amongst one group than another, or it's going to inflame the tensions in the links that already exist. And this allows us to simulate the breakdown of consensus and the increase of polarization, even within a single cohesive social network across 5 million agents. And some of the preliminary work we've done on this, we've looked at the extent to which this can even reach the level of conflict. And in some cases, this does mean, physical conflict, altercations, and death. And we've been able to get the accuracy of some of these systems up to above 90%. The most accurate system we created was 98% over a 40-year period, where it was blind to the actual data. So this is not a training data set so much as it is an optimization data set. And we're able to kind of get it there through that approach. We then can, of course, pull out what are the key features of importance. What are some of the things that are needed to be done in order to try and tamp down the conflict or address conflict, and looking at the relationship between the number of values, the amount of information in the system, and how people believe things to be quite different, right? The way you can look at one particular issue and it becomes different regardless of who you're talking to. So a bit of the next steps that we have there that are already planned even after the research is there, and different coverage. A lot of this stuff we've also really been able to look at and already start to action on. So I'm happy to get us to a point now where we can do a little bit of Q&A for the last couple of minutes if anybody has any questions.
So thank you, Justin. I will have a look in the chat. And so far, I don't see any questions. So while we wait to see if some questions come in, I would like to ask a question to you, Justin. So you touched it now in the end. What future applications do you see for AI-driven social simulations beyond policy testing? And how can policymakers use your models to improve crisis management?
No, those are great questions. Those are great questions. So to kind of look at the first one, what are the potential uses of this? The one that we are focused on is social cohesion, but a breakdown in social cohesion has a lot of subsequent effects, right? And we're currently studying what's the relationship between social cohesion and GDP with the DEC Institute. And what we're basically finding is that it seems that you have multiple percentage point loss when social cohesion breaks down. So for every sort of percentage of social cohesion that breaks down, you're also losing GDP. So utilizing just the Slovak digital twin There's policy relevance, where you can start to understand, how this could work in relationship between cohesion and GDP. But you also have investment relevance from like foreign direct investment, innovation. Slovakia is very well known for its automotive industry, for example. In the automotive industry, when they're going to invest, if there needs to be a factory built, that's $1 billion investment in a small town. So where you could place that, where there's less likely to be issues that are like culturally driven issues, becomes a critical decision for a lot of decision makers, and a lot of them are not based here. Right, a lot of the car companies are actually based in, the decisions are being made in Germany, right? And so the idea of having, the Volkswagen factory, or looking at, Jaguar Land Rover, which is a British company, when they're going to make $1 billion decision about Slovakia, they're going to create a digital twin of their factory. So they're already familiar with digital twins. So why would they not utilize a digital twin of society to help them to better understand and make that decision as well? And see, where could there be the most economic benefit? Where is there going to be a good cultural fit for a company that is in heavy industry? You're not going to want to put that everywhere, and there's certain places that are better than others where you have more compatibility there. And so that's one of the areas where I think there's that sort of dual use for this, right? And then obviously discussing this with we've already approached several political organizations like NATO about how we can use this to help fight Russian disinformation in the country. And there was a second question, but I forgot it.
Well, I think you somehow covered it. The question
Okay.
was, how can the policymakers use your models to improve crisis management? Maybe
yes.
You can add something.
Yeah. So just to kind of add on that, I mean, there's two aspects to that when dealing with policymakers that we've learned the hard way, I guess you could say. Policymakers, how can I put this nicely? Policymakers often have difficulty understanding complex scientific studies. Let me put it that way. And a lot of times they need their hand held. And there are times where it's not because they aren't smart enough. A lot of times it's just they're very busy people. And if you need to try and present this to, a minister or the head of a ministry's analytics team, you basically have a half hour of their time to give them something that they can action on. They do not care about the theory. They oftentimes do not care about the method either, not until like the second time you talk to them. Then they start to ask questions. They really want to know what are the results immediately. And so you need to interact with them, and they need to interact with this in a way that is digestible. And so, we're going to be utilizing this in an online platform that can allow them to have access to this, because they're not going to have the supercompute resources, at their institute, or the know-how at their institute to reinitialize this system and move forward. We've also agreed that because of security concerns around this, we're not going to ultimately make this model open source, because we cannot just take a model that can understand what could create more polarization in Slovakia and just let that be open sourced, so that, nefarious actors, such as Russian state agents, Chinese state agents, could use this to negatively impact the Slovak population. So for ethical reasons, we're also going to make it so that there's limited access to the model, so that people can only use it that have like a particular need for it.
So
I also see that it
now
looks
more
like we've got
questions coming in. Yes. So
Yeah.
first question from Leopoldo Silva. Maybe I can read it. As far as I understand, your simulation, digital twin, is being regular fed with real data, allowing it to respond to real conditions and prescribe actions that may react to these real-life conditions. Is that right? And if that is so, can we classify your digital twin as able to act on the society, or at least its governance?
That's a very good question. So to the first part of that question, the answer is yes. To the second part of the question, the answer is no. So yes, we are able to incorporate the digital twins in with live feeds that can come in, and that's really why Culture Pulse is brought into the discussion with Slovak Academy of Science and the DEC Institute, is that we have figured out the most efficient way to do that. I wouldn't classify it, though, as a digital twin that's able to act on society or its governance directly. There always needs to be a human in the loop there. And so we deliberately do not build out any sort of mechanisms where we're automating the output of that data to have any sort of real world effect, but rather what we're doing is using it to help decision makers better understand the repercussions of their decisions. But it is still the decision of a person, not the decision of the digital twin, that is acting on society or its governance. So I would say it's informing its governance, but it's not acting on society or its governance.
Great, thank you. We have one more question here from Tomasz Martinek. Hello, here is my question. How can your platform and invention be used to detect links between transnational crime and local diasporas? For example, language is often a key factor. Brazilian cartels, whose native language is Portuguese, operate in Portugal as an entry point to the EU for illicit drug trafficking. Their infiltration is eased by recruiting low-paid local actors who share the same language. Where does your ARIS solution intersect with this problem?
Yeah, so this is one of the things where I do think that there would be potential there. It's not something that we're actively doing, but it is something that we definitely could be doing. We have a lot of data on the individual actors, but due to the AI Act and legal compliance, we're only able to give those to security and intelligence organizations. But we are able to see, what is the language that people are posting in, who are they discussing, things with on Telegram, et cetera. And we also have those moral factors that are great predictors of people who are willing to engage in extremist behaviors, who may be willing to engage in organized crime behaviors, differentiating between, different kinds of society and why they would end up interacting. So I would say there's a possibility. It's not something that we're actively doing, but it would be a possibility through the social media monitoring that we are currently doing.
And Mark Choka is asking if you could recommend some beginner or intermediate literature in this field. Maybe this is a question for both of you. You can maybe write down in
I'll
chat
go first and then I'll let LeRon do, because LeRon's got more books that he could even kind of drop Amazon links in that he's written that he could be in there. One of them I would definitely say is one of the books that I have written actually on religion and artificial intelligence, where I outline this approach and sort of the theory and method behind it, called Understanding Religion with Artificial Intelligence, Bloomsbury. But the other ones that I always have to submit, or I always have to put up for this question, there's a series of books by Axtell and Epstein, or Epstein and Axtell, depending on which ones they are. And it's generative societies and a few other ones that maybe LeRon can find that he'll know, where Axtell and Epstein really kind of were founders in the field of agent-based models. And that can give you the theoretical and methodological foundation for agent-based models of societies, and generating artificial societies, I think, is one of them as well. That are really, really good. And they really laid the foundation for what LeRon and I do in terms of that. And so I would say, like, that's the beginner intermediary literature, is Epstein and Axtell. That's where I start with students when I'm teaching.
Great, thank you so much.
LeRon's throwing links directly into the chat there. But yeah, LeRon, I was like, I don't know if you have any other ones that you might want to throw in as good beginner books.
But in between, if LeRon also would like to answer one question for me, I would be very grateful. I wanted to ask you, how do you see cultural cybernetics evolving in the next 5 years? Where do you think is the direction heading?
Oh, that's a great question. Well, I think I guess I could say the two directions that I hope that it develops in the next 5 years. Some have already been hinted at here in terms of technical complexity and ability to do things faster with more detail. But the thing, as Justin hinted also, the thing that really drives me, that concerns me, is that it would become increasingly policy relevant. Something we worked at for many years is trying to figure out how to include the right stakeholders, diverse stakeholders, because this tool is so powerful. It gets at the causality. It provides insights into complexity in a way that no other tool does. And that tool, I feel that tool ought to be used to address societal challenges, sustainability issues, in a way that includes the most voices possible. that it's a democratic process. So my hope is that in addition to becoming more technically powerful over the next 5 years, that we crack the code, become even better at including stakeholders and policymakers that are concerned about driving these issues that enhance social cohesion.
Thank you. So I think we covered all of the topics. If anyone has more questions, please feel free to ask. If not, I would like to thank you very much to both of our speakers for their time and for sharing with us their expertise. And also thank you for all participants for joining today. As a reminder, the recording of this webinar will be available soon on our website and YouTube channel. We will also send out a short feedback form after the session, and your input is very helpful for improving future events. If you would like to stay informed about our activities, please follow NCC Slovakia online and subscribe to our newsletter. So have a great rest of your day, and we look forward to seeing you at our next event. Bye-bye.